we said that people can use that scale for the specific speed. So that scale, whether you're gonna get 20 or 40 or 80, that basically tell you, should I use axial machine or should I use impulse, right? And we said that come from this calculation. So omega in RPM, the power in horsepower, and the H is in feet, will set this number. So that explain why I told you which one require or prefer Pelton wheel, the one with high head, right? So if H is really high, what happened to the end specific speed become really small. So you will end up going here. Ouch. Okay, so the higher the head, the lower specific speed, the more you go like this. And if you have very small head, the opposite will happen. You will end up going to basically a Kaplan type or an axial machine. So Kaplan mean axial machine. Okay, and in between you will basically be radial. So if few slides ago we saw this graph. So this is another way to explain this. Basically, the head, as the head go bigger, you are preferred to use Pelton. I mean, you can still use Francis, right? And sometimes people actually use the wrong runner. They should use mixed, but they use axial for other consideration. Maybe they don't want to kill the fish, and they thought that, well, an axial machine will allow the fish to go through. So the fish is a big deal in hydraulic dams. Okay, it's in some areas for certain species that are really like salmon and stuff. Those dams gonna be really crucial because fish need to travel upstream in the river to put the eggs and come back. So guess what they do? Elevator. They make elevator for the fish. On the side, they make a place so that the fish can ride and go upstream, basically. It works. So it's a big deal, you know. So sometimes you wanna use maybe different, like, so I can imagine if you have a Pelton wheel, you'll get sushi on the other side. Right? I mean, there is no way a fish can survive basically in a Pelton wheel. Like, you got the knife, every fish cut into two parts, right? So anyway, so Pelton is very high head, right? And Kaplan is on the other extreme. But also interesting, the flow rate. So Kaplan is like all axial machine. They can deliver huge flow rate. Okay? And that's the same thing for jet engines. So if you look at jet engines from World War II until now, you'll see that in the old time, they didn't have that much flow rate, so the compressor were radial compressors. But as the engine got bigger and bigger, they cannot do radial compression anymore. They have to switch to axial compressor. Why? Because axial machine have higher flow rate. And just one look at here, you can tell why it's higher flow rate. I mean, the place is open. There's a whole flow rate can go through, right? Compared to that tight space where the high flow rate can go through, right? So in general, radial machines are higher head, smaller flow rate, and axial machine have higher flow rate and smaller head. Make sense? And if it doesn't make sense, all you have to do is just calculate the specific speed and go to this graph, and you will land in the right place. Okay? So here is another Francis turbine, and here very clear the function of the guide vanes, right? So all those guide vanes, rather than sending the flow all radial, it let the flow basically go through this place and enter with V1 theta, right? And does this passage work as a nozzle or a diffuser? Nozzle, excellent. Let me ouch. So and let me just, I wanna gonna be able to type on it. And so the nozzle part is because if we wanna plot the inlet area, it would be this, and the exit area would be like this. So you can see how this is much bigger than this. So the flow really go into a nozzle, right? This geometry basically really drop the pressure and increase the velocity. Okay, not only increase the velocity, but basically make it such that it's v1 theta basically. So the tangential component become really big. So if we are after the velocity, we still have one equation. Okay, there's nothing else but this equation. And for the power, multiply by omega. Sometimes people write the omega inside, so they end up with this u2 v theta 2 minus u1 v theta 1. Okay, to calculate the power. So this is a good time to look at the homework this week. So if we look to our homework 2, let me download this. This was in an exam 1 year, and a lot of students basically just panicked from the shape and didn't touch. But there is nothing really in this picture different than you know this is exactly this inlet guide vanes and rotor trying to eat v1 theta and try to make it leave basically with axial velocity, right? So he's saying here is the v1. So this v1 is coming because again the nozzle shape. So he's coming in with big v1 theta, and unlike our book, VR1 doesn't mean the relative velocity. VR1 mean the radial component of V1. So here in this book they say V relative for relative velocity. Okay, so it's just like V1 is split into V1 and the tangential component of V1, right? So VR1 is the radial component, and that radial component is useful to us to calculate what VR1 is used for. The radial component of the inlet velocity is useful for anyone? It's not in the v1 theta minus v2 theta thing, right? VR1 is used for m dot. VR1 is used for m dot. When we say m dot is rho AV, we decided that the velocity that we should use for m dot is the velocity normal to the area, and the area is that circumference. Make sense? Okay. So VR1 come like this, and because there is the tangential, so the rotational velocity, the plate velocity omega r1, this guy spin, and you spin with omega, and so if this is r1, then this would be omega r1. This is the u. So if this is v1, this is v1, and this is also v1. This guy is the plate velocity. So what is this? W. Excellent. The relative velocity. So plate u plus w equal v1. So that is the regular velocity diagram, right? And so this w1 is useful for or what this W1 is the same as this one, huh? We call it V relative 1. Let's call it relative velocity. So the relative velocity is useful for what? Relative velocity is the way they designed this plate for. See, if that plate is not aligned well with this W1, you will end up with a lot of losses. So the inlet of the plate need to be aligned very well with W1, with the relative velocity at the inlet. He does not see V1. V1 is aligned with the stator. The guide vane will tell you which direction is V1. But W1 is the way that basically the plate is designed for. And so will W1 change during the load or during the operation compared to, I mean, if I keep V1 constant all the time because the guide vanes are constant, will I ever have different W1? Depend on, so I'm keeping V1 the same. So if I keep the V1 the same, that probably means the flow rate is the same. But what else can change W1? Huh? So the guide vane can change the absolute velocity coming in. So as long as V1 is constant by the guide vanes, as long as those guys, as long as those guys are not changing, and you can see they can change direction if they want, right? But as long as those guys are constant, what could change W1? Anything that will change the direction of the relative velocity? If omega R1 is different. And what control omega R1? Not R1, of course, R1 is constant, but what control omega? The load. Say if the load is like really strong, the plate can slow down, right? And if the plate is basically go higher, huh? So the blade velocity could actually change WR1. So the guide vanes or the direction of the angle need to basically catch up with the change of the load so that you maintain the right W1 direction. Otherwise the plates will be horrible. Right? If you don't come right angle, you will end up basically separating and you'll have tons of friction and stuff. So anyway, so he's saying you will come with W1, and that's why the plate is basically designed like this. Okay, and the flow will leave with the plate, and that's why VR, V relative 2, will have to leave with the pipe direction, with the guide, with the trajectory, right? So V relative 2 does not have a choice but to go this way. Make sense? If you are leaving between those two plates, you just have to leave with them. If I am moving in this aisle between the wall and this, at the exit, I have no choice but to leave in the direction of the wall. So he leave with V relative like this, and V relative plus omega R2, I get V2. And if I want to do a good job in this turbine design, I should make sure that V2 is V2 should be, if I'm really doing a great job designing this turbine, I want to market this and say this is the best turbine you can ever buy in your life, then V2 need to be all radial, right? So that we consumed all the tangential momentum that we generated from V1. So you leave all radial, right? So the equation for the torque would say, yeah, m dot R1 m dot R2 V theta 2 is 0, right? There is no V theta 2. We left all radial, right? Minus R1 V theta 1, and look how much V theta 1 we got. So huge V theta 1, huh? Huge V theta 1, and almost 0 V theta 2. Okay? Make sense? Very good. So now those angle alpha and beta, traditionally people use alpha to calculate the velocity of the angle of the absolute velocity, and the beta for the relative velocity. So when you look up here, what is beta 1? That's the angle of v relative 1. And where is alpha 1? This guy. That is the direction of the absolute velocity. Okay? So you can describe the plate with the velocity diagram just by those two angles. Alpha 1 and beta 1 and alpha 2 and beta 2. Alpha for absolute and beta for relative. Okay? 1 at the inlet and 2 at the exit. Right? Make sense? Very good. So, and of course, notice that in centrifugal machine, omega R1 is way bigger than omega R2. Because, very good. So, what does he want from us? He said in the sketch V1 and alpha 1 represent the incoming absolute velocity. Yes. And with respect to the tangent of the runner. So in a pump, in a turbine they call it runner, in a pump they call it impeller, and both of them mean what? The rotor, the moving part, right? Runner for turbine, the name of the rotor, and the impeller for the pump. Okay, and V relative 1 and beta 1 represent the incoming relative velocity, sure. And the angle of the relative velocity vector with respect to the tangent runner, sure. It's required to operate the turbine at speed of 600 RPM. That is the omega. So we got our omega, 600 RPM. With a charge of 4 meter cube per second. What is the Q? It's the rho V, not rho. It's VA. The flow rate is VA. The what velocity? Which velocity? VR1. The flow rate is VR1 multiplied by that annulus, right? It's the circumference multiplied by the height. Yeah, the height of the plate or the width of the runner, right? So this charge is 4 meter and R1 is 0.6 meter and beta 1 is 75, right? And the plate height is 10 centimeter for the M dot. What should the guide angle alpha be? Okay. So I'm not going to tell you the exact number, but let's see how we're going to solve this. Alright, so what we know is, what's given to us is that the Q, which is VR1 multiplied by 2 by R1 times H. Okay, and the H is given and R1 is given and the Q is given. So from this you'll be able to calculate VR1. M dot is V time area. Make sense? Okay, and what he's asking about is this alpha. So what is required is alpha. Because alpha 2 is 0, right? So he would like to figure out what's alpha 1 from us. So in this velocity diagram, let's plot this much better here. Here is the V1 and here is, you do a good job. So here is V1 and here is U1 and this is, I'm not doing a great job here. This is W1, right? And he wants from us this angle, alpha 1. Okay? and we know V1. No, we don't know V1. We only know U1, because U1 is omega R1. So how can I get alpha 1? Help. Knowing this omega R1, and we just got ourselves this guy VR1. How can I get and we know also 75 degree. We know beta 1. Beta 1 is 75 degree. So we know this angle 75. Help. Can someone help? U1 is given, 75 degree is given, that height VR1 we just calculated it, and he's asking for this alpha 1, and we don't know V1. So this I don't know, and this I don't know, but U1 is given and VR1 is given. So the law of sines basically say what? Say that if you have a triangle and you have those angles, every length divided by the sine would basically equal to other lengths divided by the sine. So which is the length that we know? We only know U1, right? But we don't know this length, we don't know that length. But we know this angle, right? Because it's going to be 180 minus 75. Do we know alpha 1? No, we are trying to calculate alpha 1. I'm not really doing a great job explaining the geometry for you. So what we know is this distance. This is VR1. We just calculated this from where? From m dot. Okay. So this equation Q equal VR1 2 by RH1 will allow you to calculate VR1. Right? We just calculate VR1 from this. And we know U1 from omega R. So knowing this and knowing this, what else we can calculate? And knowing that this is 75 degree. Yeah, you can solve this triangle and get this. And if you know this, right, and you know U1, and you know this, of course you can get V1. So V1 square is going to be U1 square, no, it's going to be U1 plus this part, right? V relative 1 theta, I guess. The horizontal part here, that part, this square plus V relative 1 square. You got yourself V1. So now you can do the law of the sine, because you got V1 and U1, and you got basically, you can calculate the two angles. Right? Or you can just basically say, what is tan alpha? What's tan alpha 1? VR1 divided by U1 plus V relative 1 theta. So So what I'm trying to say is that this and this length decide the tan alpha, right? And this height is V relative 1, and this height is V1 plus the tangential component that you can get from 75. So this problem was all about the velocity triangle basically. Okay, and understanding that what we are looking at in that drawing, understanding that basically the U plus the V relative equal V absolute. Okay, questions? You got it? Alright. So the second problem is about the built-in wheel. Okay, and so let's go through the built-in wheel first to figure out how does it work and why the efficiency can go to really 100%. How is that possible? So in our lecture, he's saying, well, here is equations for the turbine. Now let's look at the built-in wheel bucket, and let's apply this equation to figure out the power. What do we need to apply this equation? We need V theta 1 and V theta 2, and we need U1 and U2, and we will be able to calculate the power, and let's see how large this power can get. Okay, so here is the bucket. Okay, we are looking to the bucket from I guess down or something. So the water jet is coming like this at V1. Okay, and what is that V1? That's basically all the head turning into velocity. Right, so if you apply Bernoulli equation, you'll figure out that the maximum V1 he can get is probably, of course, that nozzle will have losses in it, right? Then they will give you the loss coefficient just like a pipe or this reduction elbow have losses. But assuming you got this H and here at 1, and you are basically sending everything into kinetic energy. If you apply Bernoulli equation, you figure out that H, which is the delta Z that you have across the nozzle, will end up being all V2 square over 2G, right? So that V2 is going to be the square root of 2GH, ideally, without any losses or nozzle coefficient. Or so ideally you can apply Bernoulli between the H and atmosphere velocity is 0 and velocity is V2 without any losses, you get square root of 2GH, whereas H is the head of the dam. So now this velocity you are shooting, and there is a pocket sitting over here. So he's coming with V1, and that pocket is not fixed. That pocket is moving. That pocket is moving with omega r, right? So he is basically spinning with omega r, and so he's basically saying this: there is V1, and the plate has a kind of a U, a velocity, omega r. That U is omega r. And our velocity triangle, this time, a line. It's all straight line. Okay? Because V absolute is this, and the plate is this. And what's the equation? Plate plus relative velocity equal the absolute velocity. U plus W equal V. U plus W equal V. So whatever the difference between U and V1 is going to be the V relative 1. Make sense? Okay, and then what happened? He come straight VR1, and that's why the knife edge of the pocket. So they designed this so that the plate is aligned very well with VR1. So VR1 need to be, because it's coming axial, or what is this angle? This direction, this will be like what? tangential. It's coming all tangential. V1 is all tangential. That's perfect. All tangential. That's all we dream of. Let's make all V1 tangential. We can do that in the Bilton wheel. Notice that you cannot do this in the Kaplan and you cannot do this in the Francis. You cannot come with all tangential velocity. Because if you come with all tangential velocity on those guys, what's the problem? Why cannot come all tangential? Huh? Like this. Why cannot come? Let's make those angle, those guide vanes so that they are all, V1 is all tangential. There is no VR1. What is the problem with not having VR1? Let's make V1 all V tangential. What's the problem? You are not going to have what? No, you are not going to have, you're not going to have if V1 is all V theta, there is no V radial. You are not going to have, I'm waiting to the answer. You are not going to have flow rate. The flow will spin, but he will not get in. It's like, let's spin, guys, but no one get in because we need to be V1 theta. There is no VR1. You need to have a little bit VR to get into the pipe. Sorry, into the rotor, right? So if you just all, let's spin around, okay, let's spin around, no one get in. You need a little bit to come in. Okay? So, he will come with, here, he can do that, however. Because the entrance is all basically into the pocket is radial or tangential, sorry. The entrance to that pocket is tangential. So V1 can be all V tangential. So if in the equation when we write what's V1 theta, V1 theta will be V1. Okay? Not V1 cosine alpha 1. No, here alpha is 0. Alpha 1 is 0 because the flow is coming all tangential. Okay? And so you go into this and half of it will go to the right, half of it will go to the left, and you will basically reflect and coming back. Okay? And that is the perfect scenario. So if I wanna hit Mike super hard, I will not just make him, I will not just make the pen go and come like this and drop. No, I will make the pen come back to me. That will hurt like hell. Okay, if I hit and the pen come back to me, he get twice the mv, the mass time velocity, because he get mv minus mv, get 2 mv. He will like, that hurt, 2 mv, not just 1 mv. Okay, so that's why they send it backward. Okay, so but what is that's VR2, the relative velocity. Okay, remember our book, he called relative velocity VR. So I know that you would get confused, you think it's V radial, but no, that's his V relative, unfortunately. So this VR is V relative. So he's saying VR1, V relative 1 is basically whatever is left from V1 minus the U, and then he will come like this and he will leave with VR2. And what is the relation between the magnitude of VR2 and the magnitude of VR1? Direction wise, they are opposite to each other. He's coming like this, he leaves this way. But magnitude wise, VR2 should be same or higher or lower than VR1. A little bit lower because of the friction, not for anything else. A little bit, but theoretically speaking, VR2 is actually gonna be VR1, because the water is not gonna increase in the area or decrease in the area. Film just bounce back, but he will maintain the same velocity. If he slow down, it just slow down because of the friction on the wall. But because the the bucket is short, you can easily assume that the magnitude of VR2 is the same as the magnitude of VR1. Okay, very good. So we want to calculate the torque again. M dot R2 V theta 2 minus R1 V theta 1. We need V theta 1. We need the tangential component of the absolute velocity. So nice, you can plot VR2 for me and look at the angle. The angle is what? We said for relative velocity it's beta. For absolute velocity they use alpha. Right? So here is beta 2. But what I really need for my torque equation, I need V theta 2. Not V relative theta 2. I need the tangential component of absolute velocity. So in order to come up with V absolute 2, what he does, he need to do the equation. What's the equation? V relative plus U equal V absolute. So he say, well, here's my VR2, and where is my U? Well, same thing. The bucket was going up. We are hitting him with water. The bucket is going with the same. This part is the same as this part. They are all moving at the same velocity, right? So whatever U over here, it's the same U over there. So here is VR2 plus U equal V2. Anything you are looking that make you happy here? If there is any good news for us as designer of this machine? Does this graph or this velocity diagram make you happy in any way? V2 is very small. V2 not just very small. V2 can, if we are really careful, we can make V2 0. Okay? We can make V2 0. Let's see how is that gonna work. So he's saying, what's my goal? My goal is to get the maximum power out of this turbine. Power should be max. What does he got in his hand? He doesn't really control V1. That V1 is basically Mother Nature job. What do you mean? It's the dam upstream. Whatever the head, do we have 10 meter or do we have 100 meter? Whatever that head, square root of 2GH, that's what we're going to get at V1. But what he got as a designer in his hand is the U. He can control the U. How he control the U? The generator holding the shaft. You can make that generator very small power or very large power, right? You can make this generator basically using like, you know, trying to get 10 megawatt out of you or like 10 kilowatt. Okay? If you reduce, so here is a funny story that to explain what is going on. So when I was undergrad, my internship was in a big power plant. It was like 13 megawatt. And so the story that we had when we were doing our internship, one of the pumps that basically was taking the water from the river, they to the condenser, they have backup pumps, right? So that one is maintenance, the other one is running. And so one of them was basically into maintenance, and they just finished the maintenance, and the engineers were supposed to try it to make sure it's working before we actually disconnect the other one and make this one online. Okay, so the story was told to us was that engineer was having the power plant run all day long, 24 hours. So he had the night shift, and before he leave at 8 o'clock in the morning to go home and sleep, his boss told him, before we leave, check that the pump that came from the surface from the maintenance is running. And he turned the pump. He was like half asleep because it's like 8 o'clock, I just need to go home. And he turned the pump, the water pump that's driving the water for a 1300 megawatt power plant. Okay, so you can imagine how much water does it suck from the river basically for that condenser. He ran this pump against air. I mean, the pump was just, there was no air, there was no water in the pump. So he just turned the motor on to see if it's spinning. And so what happened? That wall that the pump was supposed to push against is not there anymore. So what happened to the pump if you turn it without water in it? What do you think happened? It spun too fast for the bearing. The bearing is not designed for that RPM. So then the bearing end up basically getting damaged. And so rumor has it that the boss actually knew that this will happen and he set him up because he hated him. So he just waited for him in the right moment. So that is a rumor. But anyway, what do we learn from that story? That in those machines, the speed, whether it's a pump or a turbine, the speed is controlled between two things, the driver and the driven part, right? So in case of a pump, the driver is the electric motor and the driven part is the water in front of it, right? So in a turbine, it's the opposite. The driver is the water and the driven is the load, the generator holding the shaft. Okay? So he can control the U. I'm telling you all the stories so that you remember that you can control the U. So now what is our choice for the U? There are two extreme cases. One extreme case is U is 0. How do you mean? How do you make U not really 0, but like 1 centimeter per second? Like it's not really moving. It's like and you can do this by making the torque on the shaft really, really big, right? So if U is 0, is that good news? No, because the power would be. Notice that U1 and U2 are the same, right? And for a built-in wheel, U1 and U2 is the same. So if we make U0 or very, very small, we get power equal to, in extreme case, very, very tiny or 0. So having huge torque, but 0 U, you will get 0 power. Doesn't work. That's the other extreme. U is maximum U that you can get is V1, and that happens if you don't have torque. If you disconnect the torque, right, that's running the turbine against zero load, basically, an ideal bearing. Then the plate will run as fast as the V1 that's hitting him. This is like kids when they get those like wheels and they blow on them, and that wheel's supposed to have like the perfect bearing. So it will rotate as fast as their jet, basically. Right? And in that scenario, if U1 equal V1, we will see that also it will end up making 0 torque, 0 power. And the reason is obvious, and that is what? If U1 equal V1, what's VR1? What's the rate of velocity? If U equal V, VR1 will be 0, so there will be the water will never catch the plate. When the velocity is the same as the plate velocity, the water will never catch like you are hitting your friend and he's running away as fast as you cannot hit him. You will never be able to catch him, right? So that's what's happening. If the water is moving as fast as the plate, or the plate is running as fast as the water, there will never be force between them. So you are not going to extract power from the turbine. Okay, so those two scenarios are going to give you 0 power. U or 0 or U equal V1. So the truth should be in the middle. And to find out what is the maximum, if you want to find the maximum of anything, what do? You write the equation for that thing in terms of the other thing. So you write the power in terms of the U, hopefully. You'll find the equation between power and U, and then you differentiate the power with respect to U and you set equal to 0. And you'll get the point of maximum power, right? And that's what he will does in the next page. So he write the power equation. What is the power? We just wrote it before. M dot. I like to write U2 V theta 2 minus U1 V theta 1, but he's basically making it the opposite because he knows that the power of a turbine will end up being negative. Why? Because we just said that the torque and V theta is negative to each other in case of a turbine, because it's a resisting torque. So he doesn't want to end up with negative power. So he said, well, I just like the magnitude of the power. I know that power of turbines is negative and the power of pumps and compressor is plus. So let me just get it in the negative form. Like let me multiply by negative so I could be plus. Okay? So that's why it's U1 V theta 1 minus U2 V theta 2, not the opposite. Does this make sense? Okay. And so you realize that U1 and U2 are the same, right? U1 and U2 are the same. They are part of the same plate. So you get U over here, and you got V theta 1 and V theta 2 over there. And he look at that velocity triangle and this velocity triangle, and he realized that V1 is U plus VR1, and over here this angle is beta 2, and he come up with those two equations for VU1 and VU2. Remember in our book the tangential component we call it VU. So the V theta we call it VU because it's the direction of the U. Okay, does this make sense? So putting those two guys here and here, he will end up with that expression for the power. This is nothing but substitution of VU1 and VU2 over here. Substituting those two guys. And here is the power as function of U. Okay? So the power as function of U is basically written like this. And now he's saying for maximum power, what do I do? D power by du. He's differentiating this equation with respect to the U, and he's setting it equal to 0. And so he end up basically showing that for this to be equal to 0, this after the differentiation. For this to be equal to 0, the only way is V1 minus 2U is 0. V1 minus 2U is 0. Or V1 is equal to 2U. Or U is equal to V1 over 2. So the maximum power, which he will substitute, he will take out the over here. So he will take out this U and he will write V1 over 2. He will take out this U and he write V1 over 2. This is the expression for the maximum power of a built-in wheel. When will you be able to get this? When you make U equal V1 over 2. So U shouldn't be 0, U shouldn't be V1, U should be V1 over 2 for maximum power. Okay, and what is the maximum power you will get? It's this expression. Okay, m dot V1 square over 4, 1 minus cosine beta over 2. Okay, so now the question in front of the house is, what if I really wanted to be even more than that? Like you got this maximum power, and now you are going to your operator, and he said, okay, set for us U equal to V1 over 2. Whatever V1 coming from that dam is, U should be half of that. So we will adjust the resisting torque so that we can make the plate always rotate at U equal V1 over 2. But what else can we do to maximize the power? Beside the U, what else? We don't control V1. We said V1 is basically just the river, whatever the head in the lake upstream from it. It's the beta. What do we want from the beta? Yeah, we want this cosine beta to be minus 1. Okay, making this beta cosine beta equal 0 is not as good as minus 1. Minus 1 is like you get what? 1 minus minus 1. Okay, so if beta 2 is 90 degree, you get cosine beta equal 0. So if the water come like this and turn this way, you got little bit. This is like hitting Mike with the pen and then the pen just drop. You don't want that. You want it to come back to you, right? You want it to be coming with minus 180. Okay, and so you imagine what happens if it's 180. What will happen if it's 180? V2 will be 0. Let's see that. Let's see if this will really work. So if this is 1 minus 1, it will be basically 2. And 2 cancel with the 4 and become, the power will be m dot V1 square over 2. The power output from that hydraulic turbine is half m dot V1 square. What is half m dot V1 square? Huh? That's all the kinetic energy coming from that hose. Your power output is exactly the power input, theoretically speaking, without any friction at the wall. Notice that the fact that we said VR1 is the same as VR2, that means that the flow on that plate is frictionless, which, you know, not really true, right? But basically what happened is we managed to consume all the V1. How? By making U equal to half V1 and by making the plate 180. Unfortunately, you cannot really make the plate 180. And the reason is, if the plate is 180, the outcoming flow would be in the direction of the incoming flow. So it's not that easier. Right? So they wanna, but they try to get it as close as possible, because you still want to send the flow out away from the incoming flow. Right? So, but the point is, hydraulic turbine, theoretically speaking, they can get 100% efficiency, because all that kinetic energy shooting from that hose can, theoretically speaking, can be slowed down to 0. Okay? So keep this in mind for the next lecture when we think, well, now what happened to the wind turbine? Can wind turbine do the same and slow down the incoming velocity all the way to 0, so that we can get 100% efficiency like those guys? Okay, so you're saying if you do 180, this become 2 and you get half m dot V1 square, and so the efficiency of course would be 100%. Okay, alright, so let's look at the homework then. So we got this one, right? You solve this triangle and you'll be able to get alpha from this over this. Now the second one was, he said there is a Spilton wheel, right? Ouch. So he got himself a built-in wheel, and he said each one of those 4 jets, okay, there's 4 of them, each one of the 4 jets strike a vein with a velocity of 100 meters per second, sorry, 100 feet per second. That's V1. Assume the magnitude of velocity of the jet remain constant along the vein surface. He's basically saying, you know, V relative 1 is the same as V relative 2. So that's what our book is doing. Please calculate the maximum power that can be extracted from this design. Maximum power. So we know that the maximum power, for maximum power, what should happen? U should be V1 over 2. Right? And we should go and actually just open our textbook and get which equation I should use. Yeah, this one, right? I should basically grab this one. I should grab this. What am I doing? I should grab this and put it here. This equation, right? So m dot is basically, so B max will end up, by B I mean power, I don't mean pressure. It's gonna be m dot V1 square over 4 1 minus cosine beta 2. Okay, so what's beta 2? Did he do 180? He didn't. He did 135. So we'll use 135. And we got our V1. So we just need the m dot. And we will be done. What's the m dot? Rho AV. Always m dot is rho AV. So last year I think what they were confused with, is it 1 jet or 4 jet? We need to do it for 4. So if this was the area of 1 jet, area jet, then you multiply by 4 jets, right? And you'll get the density of the water, of course, right? And the area of the jet, he told us it's 1 inch, so we can do that. All right? Does this make sense? Very good. So I guess one time also a problem was how we calculate the torque. If he said calculate the maximum torque or calculate the torque in this scenario. Let's say that in the midterm he said calculate the maximum power. Here is the equation for it. We got it. And the corresponding torque. How do I get the torque from this equation? And I don't want to write the R2 V theta 2 minus R1 V theta 1. I don't want to even try to calculate what's V theta 1. What's an easier way to calculate this? The torque. Yes. This power that we just calculated is torque times omega, and that omega is U over R, right? U over R1, because the omega was, the U was omega R1, right? The omega was, sorry, the U was omega R1, therefore the omega is U over R1. Make sense? So if he's after the torque, and you just calculated the thing for him, the power, you got your R1 and you got basically your U, which is, we just said for maximum power it should be how much? V1 over 2, right? So you got yourself the torque. 1 year also he said, what is the maximum torque that you can generate from this, on this shaft? How you calculate the maximum torque? He didn't say calculate the maximum power and the corresponding torque. No, he would say what is the maximum torque that this turbine can generate. So what velocity does this correspond to? U-wise. For maximum torque, U should be 0, right? And so I'm not going to be able to get it from this equation, right? Because I put U equals 0 here. That this is the maximum power. This equation is done for U equal V1 over 2. So if I want the maximum torque, I need to go a little bit up, right? I need to go up like here before I do the m dot. Sorry, before I do the differentiation, I should go here, and in this equation, this is the equation that I should copy then for maximum torque. Or so what I'm saying is this is the equation for any U. This is the equation for any U. And this equation is the torque time omega, which is U over R. So if you cancel that U with this U, you got yourself an equation for the torque. for any velocity. Right? So this is the equation for the torque for any velocity after you cancel that u and you divide over r. So now if you want the maximum torque for Tmax, you will just have to set u equal 0. So it will be m dot, and you got yourself v1 divided by r 1 minus cosine beta 2. That is the maximum torque. What did I do over here? I just made u equal 0. So this was done for u equal 0. That is the maximum torque.
Why did you divide into r?
Because that power, this is the equation for the power, and the power is torque time omega, right? I can remove that power, or write that this power is torque time omega. Omega is the RPM, radian per second. And what's the omega? Is u over r, because u is omega time r. So it's u over r. So if I like to write an equation for the torque, I just cancel this u with that u. And then I got myself an equation for the torque. And for the maximum torque, that corresponds to equal 0. And for the maximum speed, and what is the torque for maximum speed? Look at this equation for the torque. And we tell you what is the torque for maximum speed. For maximum speed, u should be v1. That's the maximum speed. And in order for u to be equal to v1, then the torque should be 0. So 0 torque, maximum velocity. 0 velocity, maximum torque. U is 0, you get the maximum torque. Torque is 0, you get the maximum speed. V1 will be u. But if you want the maximum power, if you want to get the maximum power, it's when u equal v1, and you basically get this. And if you want the corresponding torque to it, you did what I said upstairs here. Okay, I'm probably making this more confusing than it need to. So all I'm asking you to remember is that the torque time omega is the power, or basically the torque time u over r is the power. Okay, and whatever the equation for the power, you can use it to calculate the torque from it. Okay, if you write the maximum power, you get the torque corresponding to that maximum power. Very good. All right.